Okay, so looking a little bit more at evolution and some of the patterns in. Again, natural selection is one key driving force here. Named by analogy to the artificial selection where people look for features they like in domestic animals and plants. So basic idea, different individuals have more successful, useful, or less useful features. And if it survives, has offspring, and they inherit those useful traits, they'll tend to be successful as well. That feature will tend to become more common. 4 basic observations that went into that. One, there is variation between individuals. Some of those variants are helpful, some of them tend to be harmful, some of them don't matter. Living things can potentially produce more offspring than would survive. So there is a potential for overproduction, but there's only so much space in the world. There's a limit to how many actually can survive out there. Some individuals more successful produce more offspring that survive well, and so over time you're going to tend to see changes in the abundance of these different features. Among other things, this will tend to produce convergence. Different things in different parts of the world experiencing similar environmental factors, similar types of body plans and behaviors and things like that can be useful. Classic example, looking at marsupials from Australia versus the placental mammals from other continents. We have the extinct in the earlier 1900s Tasmanian wolf, built rather similar to a dog such as the familiar wolf. We have gliding tree climbing forms, similar to our flying squirrels that live around here. There are marsupial anteaters and placental anteaters slurping up things like ants and termites, colonial insects. There's the marsupial mole versus the true mole. And you have, say, in Africa, likewise, the African golden moles are quite different from the true moles as well. Aardvarks, not the same as the South American anteater. Variety of things there. Over time, some things become extinct. Maybe change in the environment, competition, diseases, predators, all these factors can lead to extinction. Different types of organisms may be more or less successful. Some vary quite a bit, like the ammonites, like the shell here. They were almost wiped out in our biggest extinction in the geologic past. Just a couple kinds made it through. Diversified, but quite dramatic ups and downs. And then finally, no, big crash again there. And then they died out with the dinosaurs. This is a graph of extinction over time. Now, there's some complications on checking the exact numbers, but you see there are ups and downs. Times we had mass extinctions, lots and lots of things all dying out at once, as well as general background turnover. Some types of things are dying out, new types are developing as we go along as well. Overall, things seem to have gotten somewhat more stable. The rate on average of extinction seems to have declined somewhat from early on towards the present. We're seeing a lot of extinctions today, largely due to the impact of humans. And some of the patterns are like what we can see in the past. Tropical species, often relatively vulnerable. Large animals often relatively vulnerable. Tropics. Conditions tend to be more stable. You don't have all the changing seasons, things like that. And so you often have more types of things, more specialized. The more specialized you are, the more vulnerable you are if something changes in what you're specialized in. Large animals, what will be challenges of being large if there's a disruption to conditions? Well, for one thing, bigger, you need more resources, more food, more space, things like that. And so finding enough food, if you're the size of an elephant, is going to be more challenging than finding enough food if you're a mouse. Large predators tend to be up at the top of the food chain. And that means if anything goes wrong further down the food chain, that's a problem. Also, if something really bad happens for a little while, and the best thing to do is go hide somewhere, again, it's a lot easier to find a hole that a mouse can hide in than a hole that an elephant can hide in. So, bigger animals do tend to be more vulnerable to extinction than smaller ones. Factors leading to extinction today, big issues, loss of habitat. If we cut down a forest or fill in a swamp, dam up a river, all these types of things mean places are no longer suited for some things to live. Of course, there's some things that we use directly, hunting, fishing, things like that. Spread of invasive species. There are things such as, say, rats and cockroaches and whatnot that do great in association with people. And things like that often tend to take over and spread and eliminate the rarer ones. A variety of patterns that we see often. One thing, Cope's rule is for body size increasing over time in a lineage. Now, it doesn't always happen. It is not a rule in that sense. Things may get smaller, things may stay the same, but it's not unusual to see a trend to get bigger over time. Of course, we tend to notice big things. You tend to get much bigger headlines for biggest dinosaur ever found than most medium-sized dinosaur found, or smallest dinosaur. Actually, that was in the headlines recently, but didn't quite get the same publicity as biggest tends to do. So we tend to notice big things, and that may bias us to thinking things that get bigger when, they're not really doing so. There are some constraints. I mean, too small and things won't function. Too big and there are problems as well. So you do get challenges there. But part of it goes with, say, again, as we saw, big things can be more vulnerable to extinction. So lineages often start out somewhat smaller. And if over time they are successful, then we might add some big things, while still having some small things as well. Some groups of organisms develop particular specializations that then works great for that purpose, but limits them in other ways. For example, elephants getting very big and a great big head on a long neck is going to be awfully heavy. Elephants characteristically have rather short necks, but then how do you reach things? And so they've got the long nose, the trunks. So this combination of things works well for being very big animals. And elephants typically are good size. Though we do see changes when elephants get to remote islands. Elephants are good swimmers. They've always got their trunks handy. And so, not too unusual for elephants to get to various island areas, but not everything makes it to islands. And so, as different types of animals get to an island, often there aren't as many predators. And so, an animal that's big and tends to depend on its size to be hard for a predator to attack. No predators. Plus, on this island, there's not as much food. Being great big, tend to get more hungry. And so, you often see where big types of animals, such as elephants, or hippos, or rhinos, or dinosaurs, tend to get somewhat smaller in island settings. You even have examples of hominids, things similar to humans, smaller in island settings. On the other hand, if you were small to begin with, and relied on your smallness to be able to hide and escape from predators, and then you get on an island, and hey, not particular predators, oh, I don't have to hide, I can get bigger. And so you often have big examples of normally small animals on islands as well. Of course, unfortunately, when a predator gets to the island, then these things are quite vulnerable. And so, for example, the various dwarf elephants, whether on the Channel Islands off of California or in various Mediterranean islands or Southeast Asia, when humans get to the island, yum! Easy to catch. The miniature elephants tend to not last very long. We can look at evolutionary relationships, patterns in the phylogeny, drawing an evolutionary tree. Sometimes there are gradual changes. These are oysters from the middle of dinosaur time, going from somewhat smaller, more tightly coiled, to a larger, broader, more bowl-shaped, not so coiled form. Other times you see quite little change. These are fish, bowfin. The living bowfin is found here in the southeastern U.S. It's a unique fish, no close living relatives. But as we go back in the fossil record, we see that, well, there's slight change, but the living ones look a whole lot like the ones that were around towards the end of dinosaur time and the like. So we've had body plan that works, and it's just kept that over a long period of time. Sometimes, instead of more continuous gradual, like was the case with those oysters, we have things basically staying the same, and then we get a point where maybe the environment changes, something else happens, and we have relatively quick change, and then we settle into something else that stays the same for a while. And that would be a more punctuated versus a more gradual model. A classic group, we can look at the patterns of change in horses. The very earliest horses, relatively small, multiple toes, living a lot in woodlands, feeding on various types of plants. As we go through time, the horses are getting bigger. Teeth are getting much bigger. Taller, more complex teeth. Grass has little bits of silica in it that the plant makes to be harder to eat. It's like having sand in your food. If you had lots of sand in your food all the time, you'd be needing some dentures before you got too old, because sand is pretty hard on the teeth. Well, horses don't know how to make dentures, so they have to have teeth that can take quite a lot of chewing on grass before they wear out. That's where the saying comes from of not looking a gift horse in the mouth. Why would you look your gift horse in the mouth? You're checking if that gift horse is an old horse, when you should be happy you got a horse. That's what the saying's about. Looking your horse in the mouth, see how worn down those teeth are. Has it been eating grass for a very long time, or is it a younger one? In addition to changing teeth for eating grass, you've got living where there is grass. And a couple of things. Grass, okay, it can be kind of tall in places, but not like trees. So hiding in grass is a little trickier. On the other hand, you can run through grass. You have a problem if you try to run through a tree. So, in areas that have more grass, less trees, fast running is a rather useful defense. And so we see horses developing longer legs and going from multiple toes to just one toe, very sturdy, strong foot, good for running. Now it's not a straight line. As you can see in this diagram, there are all sorts of branches, different forms in different parts of the world. You see some ones in different places actually sometimes converging on similar solutions. So it's not just a straight line, but over time we do have these changes. Okay, so overall, evolution, it's a interesting biological pattern, useful for biologists and anthropologists. How much relevance does it have for the rest of you? Well, living things around us are changing, and so this becomes quite important. For example, growing crops, pest organisms can evolve resistance. Medicine. We have problems right now with a virus that evolves some changes, allowing it to infect humans. And now it's spreading. There have been some changes even between the early cases and now. So there's some change in the virus. Hopefully some of those changes may be making it not so deadly, but it's changing. We have to keep up with it in medicine. Protecting rare species, understanding what will be best for them evolutionarily, protecting the genetic diversity, things like that. When we get places, say some sort of chemical dump or the like, generally bad for stuff living there, but take a look and we can sometimes find bacteria, fungi, things like that growing there that have evolved ways of breaking up the waste. And we may be able to put these to work to help clean up different types of waste, turn them into at least non-toxic stuff, maybe even useful things. Here's an example. Escherichia coli, common bacteria. There's a lot of it in our guts around, but it can become harmful. And we've seen a rather big increase over time in developing antibiotic resistance. So now this once very effective antibiotic no longer kills these germs. Being aware of evolutionary patterns in bacteria, being careful how we use antibiotics is something that's needed.